Welcome to our explainer. Today, we're diving into the hidden science that governs light itself. We're going to see how light bends, breaks, and splits apart to create some of the most beautiful and, frankly, baffling illusions all around us.
You've definitely seen this, right? You take a perfectly straight pencil, you stick it in a glass of water, and bam, it suddenly looks like it's bent or even completely snapped in half right at the water's surface. So, what's going on? It's not just in your head, it's a real trick of physics. Okay, let's get into it. Before we break down the heavy science, we're going to look at what I like to call everyday magic tricks. These are super simple experiments you can do like right now that show just how weirdly light can behave. Here's a fun one you can try at home. Put a coin in an empty bowl. Now back away from it until the rim of the bowl just barely hides the coin from your sight. Got it? Okay, stay right there and have someone pour water into the bowl. As the water fills up, the coin will look like it's lifting off the bottom and sliding right back into view. It's a fantastic little effect.
A bent pencil, a reappearing coin, both of these illusions are caused by the exact same principle. Light is actually changing its path as it moves from one substance into another. So the real question is, what's causing it to do that?
To really understand these tricks, we need to look at the rulebook that light follows as it travels through the universe. You know, this isn't magic at all. It's a fundamental property of physics, and it's called refraction. So here's the big secret. Whenever light crosses a boundary, say from the air into water or from water into glass, it bends. That's it. That's the whole trick. This bending is what we call refraction, and it's the reason for everything we've seen so far. But why does it bend? Well, it's because light doesn't travel at the same speed through everything. It's fastest in a vacuum, a tiny bit slower in air, slower still in water, and even slower when it's trying to get through something dense like glass or a diamond. When light hits that new substance at an angle, one side of the light wave slows down before the other, and that difference in speed forces the whole thing to pivot and change direction. And this bending isn't random. It follows two really simple rules. When light goes into something denser, like from air into water, it bends towards an imaginary line we call the normal. But when it goes from denser to rarer, like the light from our coin traveling from the water back into the air, it bends away from the normal. That's what makes the image of the coin travel upwards into our line of sight.
And of course, because this is physics, there's a way to calculate this perfectly. This is Snell's law. Now don't worry, we're not going to do a bunch of math here, but this really elegant formula just shows that the relationship between the angle light comes in and the angle it bends to is always a constant value for any two materials.
So that constant from Snell's law, it's directly tied to something called the refractive index, which we note with the letter N. The easiest way to think about it is as a bending power score for any given substance. The higher the refractive index, the more that substance slows light down, and therefore, the more sharply the light bends. And these scores can be wildly different. You can see air is really close to 1, almost like a vacuum. Water slows light down a decent bit, clocking in at 1.33. But then look at diamond. Its score is 2.42, which is massive. It has a huge refractive index, and that's exactly why it can bend light so dramatically. It's what gives diamonds that signature fire and sparkle. Okay, so we've got a handle on how this works in a glass of water. Now let's zoom out, way out. We're going to apply these exact same rules and see how they create illusions across our entire atmosphere. You ever look up and wonder why stars twinkle? Well, it's pure refraction. Stars are so incredibly far away that they are basically just tiny little points of light. As that single beam of light travels through miles of our turbulent atmosphere, it's passing through all these pockets of air with constantly shifting temperatures and densities. Each one of those pockets has a different refractive index, bending the light a little bit this way, a little bit that way. To our eyes on the ground, that light path is constantly wiggling, making the stars seem to flicker and dance.
So why don't planets twinkle? It's because they're so much closer to us. Through a telescope, they're not just a point, they're a tiny disk. You can think of a planet as thousands of points of light all bundled together. And while the light from each of those points is getting jostled around by the atmosphere, all those little twinkles just average each other out, giving us a nice, steady glow.
And get this, our atmosphere plays an even bigger trick on us every single day. The air is denser down here near the ground than it is way up in space, right? Well, that gradient acts like a giant lens for the whole planet. So when the sun is physically still below the horizon at sunrise, our atmosphere actually bends its light down and around the curve of the Earth, letting us see the sun about 2 minutes before it's actually there. The same thing happens in reverse at sunset. And now, for the grand finale. Let's take every single thing we've just learned, refraction, speed, and bending, and see how it all comes together to build one of the most spectacular displays in all of nature. Yep, we're gonna build a rainbow. To do this, we need one last piece of the puzzle, a concept called dispersion. See, it turns out that a material's refractive index isn't just one number. It's actually slightly different for each individual color of light. This means that when white sunlight enters something like water, each color bends by a slightly different amount. This causes the white light to split apart into a full spectrum of colors. And this is what gives us that familiar order of the rainbow. Because violet light has a shorter wavelength, it gets slowed down the most by the water, so it bends the most. Red light, with the longest wavelength, is least affected, so it bends the least. And of course, all the other colors fall right in between. Now, what's so incredible is that every single tiny raindrop acts like a perfect little prism, performing this exact three-step dance. Step 1, sunlight enters the droplet where it refracts and disperses into all its colors. Step 2, those separated colors travel to the back of the droplet and reflect off the inside surface. In step 3, the colors exit the front of the droplet, refracting one more time as they travel back into the air and towards your eyes. So here's the key takeaway. A rainbow isn't a physical thing up in the sky that you can fly to. It's an optical effect created by the sun, millions of water droplets, and your eyes, all being in the right place at the right time. Each droplet is actually sending out a full spectrum of colors, but from where you're standing, you only see one specific color from each one. All those millions of droplets at just the right angle combine to form that beautiful arc we see.
So let's just end on this thought. We've learned that stars aren't really where they appear to be. We see the sun when it isn't technically there yet. A coin at the bottom of a bowl isn't where we think it is. Since light is constantly traveling through our atmosphere with its changing density, it's always bending, even if just a tiny bit. Which leads to a pretty mind-bending question. Does that mean we never, ever see anything in its true exact position? Something to think about.